Life on Earth appeared almost the moment the planet was ready to hold it. The world had barely finished assembling itself out of dust and fire. The oceans had only recently cooled from steam into water. The sky was still thick and strange, the crust still soft in places, the days far shorter than they are now. And already, in the warm dark of those first seas, something had begun to copy itself. Some arrangement of molecules had learned the oldest trick in the universe, the trick of making more of itself from the material around it. From that quiet beginning, everything followed. Every forest, every whale, every colony of bacteria living in boiling water at the bottom of the sea, every person who has ever looked up at the night and wondered. All of it descended from that first faint stirring in the ancient ocean, and in all the vast time since, across every world we have visited and every world we have glimpsed from afar, we have never found anything else like it. That is the strange and quiet fact at the center of this story. Life began here early, and it took hold with a kind of stubbornness that suggests it might not be rare. The chemistry that built it is not exotic. The elements it uses are among the most common in the cosmos. The conditions it needed are, as far as we can tell, conditions that arise again and again on countless worlds. By every reasonable measure, life ought to be an ordinary thing, scattered like seeds through the dark. And yet, so far, we know of exactly one place where it exists. One planet out of all the numberless planets. One example from which we are trying to understand a whole universe. To ask what extraterrestrial life is, then, is to ask a question we cannot yet fully answer, using the only sample we have ever held. It is a question that sits at the meeting point of astronomy and biology, of chemistry and philosophy, of patient measurement and slow, careful wonder. It is not a question that yields to excitement. It rewards stillness. It rewards the willingness to sit with uncertainty, to hold two ideas at once, to look at the evidence gently and let it be what it is. So let the mind settle now, the way the early oceans settled, and consider the question from the beginning. Not the question of whether there are others out there watching us, or coming for us, or waiting to be found. Those are stories, and they belong to a different kind of night. The question here is simpler and deeper. What would life beyond Earth actually be? What is it made of? Where might it hide? And how would we ever know it when we saw it? These are the questions that scientists have been turning over quietly for generations, in laboratories and observatories, in the long, patient watches of the night sky. And the answers they have found, incomplete as they are among the most beautiful things the human mind has ever assembled. Begin with the word itself. Life. It is a word used so often and understood so instinctively that it comes as a surprise to learn that no one has ever managed to define it in a way that everyone accepts. A child can point to a dog and a stone and tell you without hesitation which one is alive. But turn that instinct into a precise rule, a boundary that separates the living from the non-living in every possible case, and the whole thing begins to slip through the fingers. Consider the properties that living things seem to share. They take in energy from their surroundings and use it to maintain themselves, holding back the slow drift toward disorder that governs everything else. They grow. They respond to the world around them. They carry information, a set of instructions written into their chemistry, and they pass that information on to a new generation. And crucially, over long stretches of time, they change. The instructions are copied imperfectly. Small variations creep in, and those variations that help a thing survive and reproduce tend to spread. This is evolution by natural selection, the slow sculpting force first described by Charles Darwin, and it is perhaps the single most important feature of life as we understand it. When scientists at the Space Agency needed a working definition of life, something to guide the search for it elsewhere, they settled on a phrase that leans heavily on that last idea. Life, in this definition, is a self-sustaining chemical system capable of Darwinian evolution. A system that keeps itself going, drawing on the world for energy and material, and that is able to evolve across generations. It is a spare and careful definition. It says nothing about cells, nothing about carbon, nothing about water, blood, or breath. It tries to describe not the particular life we know, but the essence that any life anywhere might share. Even so, it is not a perfect definition, and the scientists who use it are the first to admit as much. It sits awkwardly at the edges. A virus, for instance, carries genetic information and evolves with remarkable speed, yet it cannot reproduce on its own. It must hijack the machinery of a living cell to make copies of itself. By some readings, it is alive. By others, it is not. And the honest answer is that it lives in the borderland between the two. A single sterile creature, an animal that cannot reproduce, still seems fully alive to us, and yet it evolves nothing. A crystal growing in a mineral solution copies its own structure endlessly and sustains a kind of order, yet no one would call it a living thing. The definition captures something true and important, but it does not draw a clean line, because there may be no clean line to draw. Life may not be a single sharp category so much as a gathering of properties that tend to travel together, present in full in the things we know, and perhaps present in stranger combinations in things we have not yet met. This matters more than it might seem because it shapes the entire search. If we are looking for life beyond Earth, we must first decide, at least roughly, what we are looking for. And the danger is always the same. It is the danger of looking only for ourselves, of assuming that life everywhere must be built the way life here is built, must breathe what we breathe, must fill the same narrow band of temperatures and pressures that suits our own soft bodies. The history of this search has been, in large part, a slow and humbling education in how much wider the possibilities might be. Again and again, life on our own planet has turned out to be stranger and harder than anyone expected, and each surprise has widened the circle of places where life elsewhere might be found. But before turning outward, it is worth staying with the one example we have and asking how it is built. Because whatever else may be true of life across the universe, the life we know is made of particular stuff, arranged in particular ways, and understanding that arrangement is the closest thing we have to a map. The first thing to notice is how few ingredients life actually requires. For all its staggering variety, from the smallest microbe to the largest tree, life on Earth is assembled from a short list of chemical elements. 6 of them do most of the work: carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. These 6, in various combinations, make up the overwhelming bulk of every living thing that has ever existed. And what is striking, when you step back, is that these are not rare or precious elements, hoarded in some obscure corner of creation. They are among the most abundant elements in the universe, forged in the hearts of stars and scattered across space when those stars die. The material of life is, quite literally, everywhere. Of these 6, one stands apart. Carbon is the element around which all the rest are arranged, the central thread from which the molecules of life are woven. And the reason for carbon's importance lies in a simple feature of its structure. A single carbon atom can form 4 bonds with other atoms, and it can form those bonds not only with other elements, but with other carbon atoms, joining them into chains and rings and branching structures of almost limitless complexity. Carbon is the great connector, the element that can build long, stable molecules with the flexibility to hold information and carry out the intricate chemistry that living things depend on. When scientists speak of organic chemistry, they mean, at bottom, the chemistry of carbon. It is no accident that the search for life beyond Earth so often becomes a search for carbon-based molecules, for the organic compounds that are, if not life itself, at least the raw material from which the only life we know is made. Alongside carbon stands water, not as a building block in the same way, but as a setting, a medium, the liquid in which the chemistry of life takes place. Water has a set of quiet, almost hidden properties that make it extraordinarily well suited to this role. It dissolves an enormous range of substances, allowing the molecules of life to meet, mingle, and react. It remains liquid over a fairly wide temperature range. It moderates heat, warming and cooling slowly, buffering living things against sudden change. So central is water to life as we know it that the search for habitable worlds has, for decades, been guided by a single phrase: follow the water. Find liquid water, the reasoning goes, and you have found at least one of the essential conditions that life on Earth requires. It is not a guarantee. Water alone does not make life, but it is a starting point, a first thing to look for in the dark. There is a third requirement, quieter than the other two but no less essential: energy. Life is a process that runs against the current. Everything in the universe tends, over time, toward disorder, toward evenness, toward the cold and formless spreading out of heat and matter. A living thing holds itself apart from that drift, maintaining its structure, repairing its damage, keeping its intricate order intact. And to do that, it must constantly draw energy from its surroundings. On Earth, most life ultimately runs on sunlight. Plants and certain microbes capture the light of the sun and use it to build the sugars that feed nearly everything else. But sunlight is not the only source. In the deep ocean, far below the reach of any light, whole communities of living things draw their energy from chemistry alone, from the reactions between minerals and water at the hot vents on the sea floor. Wherever there is a source of energy and a way to tap it, life has found a way. And this, too, reshapes the search. A world need not be bathed in the light of its star to be habitable. It needs only to have a steady flow of energy that life could learn to drink. Carbon, water, energy. These are the pillars of life as we understand it, the conditions that the one biosphere we know requires. And with them in mind, the deepest question of all comes into focus. Not where life might be found, but how it began. Because if we could understand how life started here, even once, we would understand a great deal about how likely it is to have started elsewhere. This is one of the oldest questions there is, and for most of human history, it lay entirely beyond the reach of science. Life came from life. That was all anyone could say. Every living thing was born of some other living thing, in an unbroken chain stretching back beyond memory. But the chain could not stretch back forever. There was a time, early in the planet's history, when there was no life at all, only rock and water and the raw chemistry of a young world. And then, at some point, there was life. Something crossed the line. The great question is how. The modern effort to answer it began, in a sense, with an idea sketched out in the early part of the 20th century by two thinkers working separately, a Russian named Alexander Oparin and an Englishman named John Haldane. They proposed that the early Earth, with its atmosphere unlike the one we breathe today, might have been a place where the building blocks of life could form on their own. Energy from lightning and sunlight, they suggested, acting on the simple gases of the young atmosphere, might have driven the creation of more complex molecules, which gathered over long ages in the seas, until the oceans became a kind of thin broth of organic compounds. This idea came to be known, in a phrase that has lasted far longer than perhaps it deserves, as the primordial soup. For years, it remained just an idea, elegant but untested. Then, in the early 1950s, a young researcher named Stanley Miller, working in the laboratory of the chemist Harold Urey, decided to try it. He built a small, sealed apparatus of glass, a closed loop of flasks and tubes. Into it, he placed water, to stand for the ancient ocean, and a mixture of simple gases thought to resemble the early atmosphere. Then he sent electric sparks through the mixture, again and again, standing in for the lightning of a young and stormy world. He let it run, and he waited, and he watched the clear water slowly darken. When at last he analyzed what had formed inside the flask, he found something remarkable. Amino acids, the very molecules that living things use to build proteins, had appeared out of nothing more than gas and water and a spark of energy. Life had not been created in that flask, but some of its most basic ingredients had assembled themselves, unbidden, from the plainest of beginnings. The experiment was a landmark, and its result has been repeated and expanded many times in the years since. It showed that the raw materials of life are not difficult to make. Given the right conditions, they seem to form readily, almost eagerly, from simple starting chemicals. And in the decades that followed, this same lesson arrived from unexpected directions. The building blocks of life, or molecules very close to them, have been found in meteorites that fell to Earth from space, in the frozen comets that wander the outer solar system, and drifting in the great cold clouds of gas and dust that float between the stars. The chemistry that leads toward life appears to be woven into the fabric of the cosmos itself, playing out quietly wherever the ingredients gather. The building blocks, it seems, are common, but building blocks are not a building, and here the story grows harder and more honest and considerably more uncertain. It is one thing to make amino acids. It is quite another to assemble them, along with all the other molecules of life, into a system that can feed itself and copy itself and evolve. Between the primordial soup and the first living cell lies a gap that no one has yet fully bridged, and the crossing of it remains one of the great open problems of science. What we have, instead of a single answer, is a set of thoughtful and competing ideas, each capturing part of what must have happened, none of them yet complete. One of the most influential of these ideas concerns a molecule called RNA. In the cells of living things today, the flow of information runs in a well-defined direction. Instructions are stored in DNA, that famous double spiral, and carried out by proteins, the workhorse molecules that do nearly everything a cell needs done. RNA sits in the middle, usually acting as a messenger between the two. But RNA has a curious double nature. Like DNA, it can carry genetic information, and like a protein, it can, in certain forms, drive chemical reactions. It can be both the message and the machine. This has led many researchers to suspect that the earliest life ran on RNA alone, before DNA and proteins had taken up their specialized roles. In this view, there was once an RNA world, a stage in which molecules of RNA copied themselves and slowly evolved, long before the familiar machinery of modern life appeared. It is a compelling idea, supported by real clues in the chemistry of living cells. But it, too, is incomplete, because RNA is a complicated molecule, and how the first strands of it came together on the early Earth remains difficult to explain. Others have looked not to the surface seas, but to the deep ocean floor, and to the strange structures that rise there in the dark. At certain places on the sea bottom, where mineral-rich water seeps up through the crust, tall chimneys form, venting warm fluids into the surrounding cold. Some of these vents are searingly hot and acidic, but others, of a gentler kind, are warm and alkaline. And around them, the water and rock react in ways that release usable chemical energy. It has been proposed that in such places, sheltered from the harshness of the surface, with a steady flow of energy and a natural scaffolding of porous rock in which molecules could gather and concentrate, life might have taken its first steps. The most studied of these gentle vent fields carries the name of a lost city, and the chemistry that unfolds within it bears an intriguing resemblance to the deepest and most ancient chemistry of life. Whether life truly began at such vents, or in warm pools at the surface, or somewhere else entirely, remains an open question, argued back and forth as new evidence arrives. And there is a further possibility, stranger than the rest, which is that life did not begin on Earth at all. This idea, known as panspermia, does not claim to explain how life first arose. It only suggests that life, or its precursors, might have formed somewhere else and traveled here, carried across space inside comets or meteorites, seeding the young Earth from beyond. It is not as far-fetched as it first sounds. We know that rocks are blasted off the surfaces of planets by great impacts, and that some of them wander the solar system for ages before falling elsewhere. We know that certain hardy microbes can survive extraordinary extremes of cold, radiation, and vacuum. Whether any living thing could truly survive such a journey, and whether it ever did, we do not know. And even if it were true, it would only push the question back a step, from where did life on Earth begin to where did life anywhere begin? But it is a reminder that the worlds of the solar system are not sealed off from one another. Material moves between them, and if life ever arose on more than one of them, it need not have arisen entirely alone. What all these ideas share, beneath their differences, is the recognition that the origin of life was a chemical event, something that happened when ordinary matter, under the right conditions, crossed over into the living. And this returns us to that quiet fact from the beginning, the one that gives the whole search its charge. Life appeared on Earth early. The planet formed about 4.5 billion years ago out of the disk of debris that circled the young sun. For its first several hundred million years, it was a hostile place, its surface repeatedly melted by great impacts, its oceans perhaps boiled away and reformed more than once. And yet the earliest traces of life reach back to somewhere around 3.5 billion years ago, and possibly earlier still. Which means that, more or less, as soon as the Earth had cooled and steadied enough to permit it, life was already here, not billions of years later after some long and unlikely wait, but quickly, in geological terms, almost at once. That speed is a clue, though a clue that must be read with care. One reading of it is hopeful. If life arose so readily here, the reasoning goes, then perhaps it arises readily wherever the conditions allow, and the universe may be quietly alive in a great many places. But there is a caution buried in that hope, and it is a caution worth sitting with. We have only one example. We know of exactly one world where life exists, and it is the world we are standing on, the world from which we are asking the question. A single example is a treacherous thing to reason from. It might be that life is common, and Earth is ordinary. It might equally be that life is vanishingly rare, and that we exist to ask the question only because, on this one world among countless others, the improbable happened. From inside a single example, the two possibilities can look almost the same. We cannot yet tell them apart. And this is precisely why the search matters so much. A second example, anywhere, of any kind, would transform the question from philosophy into science. It would tell us, at a stroke, that life is not a one-time accident, but a repeatable feature of the universe. Until then, we reason from one, and we do so gently, aware of how little one can teach. There is, though, one more lesson that the single example of Earth has taught, and it is perhaps the most important of all for the search. It concerns not how life began, but where it can survive. For a long time, the boundaries of life seemed obvious. Life needed sunlight, or something fed by sunlight. It needed moderate temperatures, neither freezing nor scalding. It needed air and fresh water, and conditions not too far from those a human being would find comfortable. The living world, as people understood it, was a thin and gentle skin stretched across the surface of the planet, confined to the places where the weather was mild and the light reached down. That picture, over the last several decades, has been quietly and thoroughly demolished. And the ones who demolished it are among the humblest organisms on Earth, the single-celled forms of life that scientists have come to call extremophiles, the lovers of the extreme. They turn up in places that ought to be lethal. In the boiling water of hot springs, where the heat would cook any ordinary cell, there live microbes that thrive at temperatures near the boiling point, and some that prefer it hotter still, clustered around the scalding vents of the deep sea floor, in the frozen valleys of the polar regions, in ice that never melts. Other microbes go about their slow business in the cold. There is life in water so acidic it would dissolve metal, and in water so alkaline it would burn the skin. There is life in the crushing dark of the deepest ocean trenches, under pressures that would flat a submarine. There is life in pools so salty that almost nothing else can grow, life inside solid rock miles beneath the surface, feeding on nothing but the chemistry of the stone, life in the cooling water of nuclear reactors, life that shrugs off doses of radiation that would kill nearly anything else many times over. Some microbes can dry out completely, halting all their processes, and lie dormant for years or longer, only to revive when water returns. Wherever there is a scrap of energy and a trace of the right chemistry, in almost any conditions the planet can offer, something has found a way to make a living. The significance of this for the search beyond Earth is difficult to overstate. Each of these discoveries widened the circle. Each one said, in effect, that a place we had written off as dead might in fact be habitable, if life elsewhere is as resourceful as life here. A frozen world, an ocean sealed under ice, a planet without sunlight, a moon baked in radiation, a world of acid and salt and crushing pressure. Every one of these, once dismissed as impossible for life, now had to be reconsidered. The extremophiles taught a lesson in humility. They showed that our sense of what life requires was shaped too much by our own comfort, and that the true limits of life are far wider than we had dared to guess. When scientists now look out at the strange and hostile worlds of the cosmos, they do so with the memory of these organisms in mind, unwilling to assume that any place is truly beyond the reach of the living until they have looked and found it empty. And so the search for life beyond Earth is, in a real sense, a search guided by the extremes of life at home. It asks not where life would be comfortable, but where life, at its hardiest and most inventive, could possibly hold on. That question has a longer list of answers than anyone once imagined. But to organize the search, scientists needed a place to begin, a first principle for deciding which of the numberless worlds in the sky deserved a closer look. And the principle they settled on, for all its limits, has shaped the exploration of the cosmos for a generation. It is the idea of the habitable zone. The reasoning behind it is straightforward, and it returns once more to water. If liquid water is essential to life, or at least to life of the kind we know, then a world can only be habitable if it is capable of holding liquid water on its surface. And whether it can hold liquid water depends, more than anything else, on its distance from its star. Too close, and the star's heat boils the water away, leaving a scorched and desiccated world. Too far, and the water freezes solid, locked into ice that never melts. But at a certain range of distances, neither too near nor too far, a world might be just warm enough for water to remain liquid, pooling in oceans and lakes and rivers as it does on Earth. This comfortable band, this ring of moderate distances around a star, is the habitable zone. In a nod to an old children's story, it is sometimes called the Goldilocks zone, the region where conditions are not too hot and not too cold, but somewhere in between. It is a useful idea, and it has done real work. It gives astronomers a way to sort through the growing catalog of worlds beyond our solar system and to say, of each one, whether it falls within its star's habitable zone or outside it. It focuses attention and resources on the worlds most likely to reward a closer look. But it is also, its own advocates are quick to admit, a crude and partial measure, and it can mislead as easily as it can guide. Being in the habitable zone is not the same as being habitable. A world in the right place around its star may still be lifeless for 100 reasons. It may have no atmosphere, or the wrong kind, or an atmosphere so thick that it traps heat and roasts the surface far beyond what its distance alone would suggest. It may lack water entirely. It may be blasted by radiation from a violent star. It may be a ball of gas with no surface at all. The habitable zone tells us only that a world is at a distance where surface water is not immediately ruled out. It tells us nothing certain about what that world is actually like. And the deeper trouble is that the habitable zone, defined by surface water and starlight, misses some of the most promising places of all. The extremophiles have shown that life does not require a sunlit surface. It can live in the dark, on chemical energy, in water sealed away from any star. And as it happens, some of the most tantalizing candidates for life in our own solar system are worlds that lie far outside the traditional habitable zone, cold and distant. And yet, beneath their frozen surfaces, they may hide oceans of liquid water, warmed not by a distant sun, but by forces within. To understand those worlds, and the broader search they represent, it helps to come home first, to the handful of worlds close enough to visit, and to ask what the exploration of our own solar system has revealed. Mars has always been the nearest and most natural place to look. It is a small, cold, rust-colored world, half the size of Earth, orbiting a little farther from the Sun. Today, its surface is a frozen desert, its air thin and dry, its temperatures brutally low, a place where liquid water cannot last on the surface, quickly freezing or boiling away into the near vacuum of the atmosphere. But Mars was not always this way. The evidence for that lies written across its surface, in features that only water could have carved. There are dry riverbeds that once carried flowing streams. There are the outlines of ancient lakes and the fan-shaped deposits of old river deltas, where sediment settled out of moving water just as it does on Earth. There are minerals that form only in the presence of water, spread across regions of the planet. Billions of years ago, it seems, Mars was a warmer and wetter world, with rivers and lakes, and perhaps even seas, under a thicker atmosphere and a milder sky. And if the surface of Mars once held liquid water for long stretches of time, then Mars once had, however briefly, the conditions that life on Earth required. This is why so much effort has gone into exploring it. A succession of robotic craft has been sent across the void to circle Mars and to land upon it, each generation more capable than the last. Orbiters have mapped its surface and sniffed its thin air. Rovers have crawled across its plains and up the slopes of its craters, drilling into rock, studying the chemistry grain by grain. Along the way, they have found, again and again, the fingerprints of that ancient water, and they have found something more. They have found organic molecules, the carbon-based compounds that are the raw material of life, preserved in the ancient sediments. This does not mean they have found life. Organic molecules can form without life, through ordinary chemistry, and they arrive on Mars in meteorites and dust from space as well. But their presence confirms that the ingredients were there, in a place where water once flowed, in exactly the kind of setting where, on Earth, life took hold. There has been another tantalizing signal too, and it concerns a gas. Traces of methane have been detected in the Martian atmosphere, and the amount seems to rise and fall with the seasons in ways that are difficult to fully explain. This is intriguing because, on Earth, much of the methane in the air is produced by living things. But methane can also be made by ordinary geological processes, by reactions between rock and water deep underground, with no life involved at all. The Martian methane remains a genuine puzzle, its source still debated, its meaning uncertain. It is exactly the kind of ambiguous clue that has made the study of Mars both thrilling and endlessly careful. A hint, but not an answer. The most recent chapter in this long investigation has unfolded in a crater called Jezero, a great bowl that billions of years ago held a lake fed by an ancient river, its delta still visible where the water once spilled in. A rover named Perseverance was sent there precisely because it was once a place of water and sediment, the sort of place where signs of ancient life, if any exist, might be preserved. And in the summer of a recent year, working its way across a formation of layered rock, the rover came upon a stone that has since drawn intense attention. The scientists named the rock for a feature of the Grand Canyon, and from it, the rover drilled a core sample, sealing it away in a sterile tube. What made this rock remarkable was the pattern of markings across its surface. There were small dark spots, which the scientists likened to poppy seeds, and larger spots, pale in the center with dark rims around them, which they called leopard spots. On Earth, patterns like these can form when certain chemical reactions take place in wet sediment, reactions of a kind that can be driven by microbial life, the sort of chemistry that microbes use to draw energy from their surroundings. The rock also held the ingredients that such life would need. It contained clay and silt, the fine sediments that preserve delicate features. It contained organic carbon. It contained iron, phosphorus, and sulfur, elements that living things use. Everything about it, the setting, the chemistry, the strange patterned spots, lined up in a way that pointed, cautiously, toward the possibility of ancient life. After more than a year of careful analysis, the team announced their findings, and the phrase they chose was chosen with great precision. They had found, they said, a potential biosignature. A potential biosignature is not proof of life. It is a feature, a chemical, a structure, or a pattern that could have been made by living things, but that might also have been made by processes with no life involved. The word potential carries the whole weight of scientific caution. It says, we have found something that life could explain, and we have looked hard for ways to explain it without life, and we have not found a wholly satisfying one, but we cannot yet rule those explanations out. It is one of the strongest such signals ever found on Mars, and at the same time, it is not a discovery of life. It is a candidate, a rock that deserves the most careful scrutiny science can bring to bear. And there lies the difficulty, because the most careful scrutiny cannot be performed on Mars. A rover, for all its instruments, is limited. The truly decisive tests, the fine analysis of isotopes and mineral structures, and the microscopic texture of the rock, require laboratories of a kind that cannot be flown to another planet, laboratories full of large and delicate instruments and human hands. To settle the question, the sample would have to be brought back to Earth. And so the patterned rock now sits, sealed in its tube, waiting. There are plans to retrieve it, to send a craft to Mars to gather the cached samples and carry them home across the solar system. But such a mission is enormously difficult and enormously expensive, and its future has been clouded by questions of cost and schedule. For now, one of the most scientifically precious objects in the search for life beyond Earth rests quietly on the surface of another world, a promise not yet kept, an answer not yet read. This is the honest shape of the search on Mars. Not a moment of triumphant discovery, but a slow accumulation of suggestive evidence, each piece carefully weighed, each conclusion hedged with the caution that the stakes demand. Ancient water confirmed, organic molecules confirmed, seasonal methane puzzling and unresolved, patterned rocks that could be the traces of ancient microbes, or could be the work of lifeless chemistry, waiting for a verdict that may not come for years. It is a portrait of science working exactly as it should, refusing to leap ahead of its evidence, holding the extraordinary possibility at arm's length until the proof is truly in hand. And whatever the patterned rock turns out to be, the deeper lesson of Mars is already clear. There was a time when the young Mars and the young Earth were not so different, two rocky worlds with water and warmth and the ingredients of life. On one of them, life arose. Whether it also arose on the other, even faintly, even long ago, is a question that the red planet has not yet finished answering. If Mars represents the search for life on a world that was once warm and is now cold, then the moons of the outer solar system represent something stranger, and in some ways, more hopeful. For out there, far beyond the traditional habitable zone, in the cold reaches around the giant planets Jupiter and Saturn, are worlds that appear, against all expectation, to hold vast oceans of liquid water, not on their surfaces, which are frozen solid in the deep cold, but beneath them, sealed under shells of ice, hidden from view and from the light of the distant sun. These are the ocean worlds, and they have quietly become some of the most promising places in the entire solar system to search for life. Consider Europa, one of the 4 large moons of Jupiter, a body slightly smaller than our own moon. Its surface is a shell of ice, smooth and bright and crisscrossed with a network of long, dark cracks, one of the smoothest surfaces of any world we know. And beneath that ice, the evidence strongly suggests, lies an ocean, not a small one. Europa's hidden sea is thought to hold more than twice as much water as all the oceans of Earth combined, a global ocean wrapped entirely around the moon, dark and deep and utterly sealed. The evidence for it came first from a spacecraft named Galileo, which orbited Jupiter for years and studied its moons, detecting the subtle magnetic signs of a salty, electrically conductive layer beneath Europa's ice. The question that follows is where the warmth comes from, out there in the deep cold, so far from the sun. And the answer lies in the great planet Europa's circles. As the moon orbits Jupiter, the immense gravity of the giant planet pulls and stretches it, flexing its interior, kneading it like a ball of clay worked in the hands. That constant flexing generates heat within the moon, heat enough, it seems, to keep an ocean liquid beneath the frozen crust. This process, called tidal heating, is a source of energy that owes nothing to sunlight. It is a way for a world far outside the habitable zone to stay warm within, to hold liquid water in the dark. And where there is liquid water, and energy, and the right chemistry, there is at least the possibility of life. Europa may have all 3. The water is nearly certain. The energy from tidal heating is there. And the chemistry may be there as well, for the ocean is thought to be in contact with a rocky sea floor below, where reactions between water and rock could supply the chemical ingredients and the chemical energy that life could use, much as life clusters around the vents on Earth's own ocean floor. There is even a tantalizing possibility that material from the surface, altered by Jupiter's fierce radiation, might work its way down into the ocean. And that material from the ocean might rise to the surface through the cracks, so that the sealed sea is not entirely cut off from the world above. All of this makes Europa a place of extraordinary interest. An ocean, kept liquid by the tides, resting on rock, perhaps stirred by the slow exchange of chemistry between the deep and the surface. If life could take hold in such a place, Europa might be exactly the kind of world where it would. To learn more, a spacecraft has been sent. Launched in the autumn of a recent year, it is the largest craft of its kind ever built for a journey to another world, and it carries a suite of instruments designed to study Europa in detail. It will not land, and it is not, strictly speaking, a mission to detect life. Its purpose is more careful than that. It is a mission to determine whether Europa is habitable, whether the conditions for life are truly present beneath the ice. It will not arrive for years, for the journey to Jupiter is long, and once there, it will not simply circle Europa. For the radiation around the giant planet is so intense that it would quickly destroy the craft. Instead, it will orbit Jupiter and make dozens of close passes by the moon, studying its ice and its hidden ocean a little more with each approach. It is patience made into a machine, sent across the solar system to answer, slowly, one of the oldest questions there is. Farther out still, circling Saturn, is a world smaller than Europa, but in some ways even more astonishing. Its name is Enceladus, and it is a tiny moon, only about 500 kilometers across, small enough to fit within the length of many countries. Its surface a brilliant white shell of clean ice. For a long time, it seemed too small and too cold to be of much interest. Then a spacecraft named Cassini, which spent years studying Saturn and its moons, made a discovery that changed everything. From great cracks near the south pole of Enceladus, it was found that enormous plumes of water were erupting into space. Jets of water, vapor, and ice, spraying up from the interior, feeding a faint ring of material around Saturn, venting continuously into the dark. Enceladus was not a dead ball of ice. It was geologically alive, and it was leaking its interior into space where a passing spacecraft could sample it directly. And so Cassini flew through the plumes again and again, tasting what the little moon was throwing out. What it found was remarkable. The plumes carried water, confirming an ocean beneath the ice. They carried salts of the kind that would dissolve from a rocky sea floor, suggesting the ocean was in contact with rock. They carried tiny grains of silica that hinted at hot water reacting with stone deep below. The signature of hydrothermal activity, of warmth and chemistry at the ocean's base. And they carried organic molecules, the carbon-based compounds of the kind that life is built from. In a later and more careful study of the data gathered during the closest and fastest passes through the plumes, researchers identified an even richer collection of these organic compounds, including molecules of the sort that, on Earth, form parts of the membranes that enclose living cells. Here, then, was a small frozen moon that seemed to have everything. Liquid water in a global ocean beneath the ice, energy and warmth from hydrothermal activity at the sea floor, and a rich stock of organic chemistry, the raw material of life. All three of the pillars present together on a world that fits inside the width of a modest country, so far from the sun that its year lasts 3 decades of hours. And most remarkable of all, this ocean does not need to be reached by drilling through miles of ice. It sprays itself into space, offering samples of an alien sea to any craft willing to fly through the mist. Even here, though, the caution holds, and a recent line of research shows exactly why it must. Some of the organic molecules found in the plumes, it has been suggested, might not come from the ocean at all. They might be formed near the surface or in space by the action of radiation on simpler compounds, chemistry with no life involved. The presence of organic molecules, once again, is not the presence of life. It is the presence of life's ingredients, which is a different and lesser thing, and telling the two apart is one of the central challenges of the whole endeavor. Still, few places in the solar system are as inviting as Enceladus. There is serious discussion of sending a craft back to Saturn to fly through the plumes with instruments far more sensitive than any that have gone before. Perhaps even to land near the erupting cracks and study what pours out. If there is life in that hidden ocean, its traces may already be drifting into space, waiting only for something clever enough to read them. There is one more moon that deserves a place in this account, and it is perhaps the strangest of them all. It is Titan, the largest of Saturn's moons, a world bigger than the planet Mercury, and the only moon in the solar system wrapped in a thick and substantial atmosphere. That atmosphere is denser than Earth's own, and like Earth's, it is made mostly of nitrogen. Beneath it, hidden for a long time under a golden haze, lies a landscape that is at once eerily familiar and profoundly alien. Titan has weather. It has clouds, rain, and wind. It has rivers that carve channels, and lakes and seas that pool in its lowlands, and a cycle of evaporation and rainfall, much like the water cycle of Earth. But the temperature at Titan's surface is so low, close to -180 degrees on the Celsius scale, that water there is frozen as hard as rock. The liquid that falls as rain and gathers into seas is not water at all. It is methane and ethane, compounds that on Earth are gases, but that in the deep cold of Titan flow as liquids across the surface. This makes Titan a natural laboratory for one of the boldest questions in the whole search. All the life we know uses water as its liquid medium, the setting in which its chemistry unfolds. But is water truly necessary, or is it simply what was available here? Could some other liquid serve the same role on some other world? Titan, with its seas of liquid methane, poses that question directly, and it has led to a genuinely radical idea, which is that life might exist in those frigid seas, built on a chemistry utterly unlike our own, using liquid methane where we use water, and molecules quite different from the ones that make our cells. The idea deserves to be treated with care, because it stands at the far edge of what science can currently say, and it is speculation, clearly labeled as such by the very people who explore it. But it is thoughtful speculation, grounded in real chemistry. Some years ago, researchers proposed that a particular molecule, one that has actually been detected in Titan's atmosphere, might be able to assemble itself into tiny hollow spheres in liquid methane, structures that would work something like the membranes that enclose living cells on Earth. If such structures could form, they might provide the little compartments that any life would seem to need, a way to keep the inside separate from the outside. It was a striking suggestion, and it gave the dream of life on Titan a foothold in real molecules. Yet science, working as it should, has pushed back on the idea. Later studies, first through computer modeling and then through laboratory experiments, have raised serious doubts about whether those membranes could actually form under Titan's conditions. The most recent work suggests that the proposed molecule behaves differently than the original idea required, and that if life exists on Titan, it would need some other, still unknown foundation. The dream is not dead, but it is contested, an open argument at the frontier of the possible. There is also, on Titan, a second and more familiar possibility. Deep beneath its icy surface, the same tidal forces that warm the other moons may maintain an ocean of ordinary liquid water, another hidden sea in the outer solar system. So Titan may, in fact, offer two chances at life: an exotic, unproven kind in the methane seas at the surface, and a more conventional kind in the water ocean sealed below. A spacecraft is being prepared to go there, an extraordinary machine, a flying rotorcraft that will soar through Titan's thick air and set down at different sites across the surface, studying the chemistry of this frozen world in detail. It is not designed to find life directly. Its aim is to understand how far the chemistry of Titan has progressed toward life, to read the record of complex organic compounds written across its dunes and plains, and so to learn something about the chemical steps that might lead, on some world somewhere, from lifeless matter toward the living. It will be years before it arrives. Titan keeps its secrets slowly, at the far end of a very long journey. Closer to home, in the opposite direction, lies a world that is in almost every way the opposite of frozen Titan, And yet it too has been drawn into this search in a way few expected. It is Venus, the second planet from the Sun, a world nearly the same size as Earth and once imagined to be a warm and cloudy sister to our own. The reality, revealed by the spacecraft that have visited it, is far harsher. The surface of Venus is the hottest of any planet in the solar system, hot enough to melt lead, hidden beneath a crushing atmosphere of carbon dioxide many times denser than our own, and wrapped in thick clouds not of water, but of sulfuric acid. It is, at the surface, about as hostile a place as can be imagined for any living thing, a landscape of baking rock under a sky of poison and pressure. No one seriously looks for life on the surface of Venus, but high above that surface, some 50 kilometers up in the clouds, the conditions change. The temperature drops to something more moderate, and the pressure eases towards something more like the surface of Earth. And it is there, in that narrow layer of the Venusian sky, that a small number of scientists have wondered whether some hardy form of microbial life might drift among the clouds, floating in the acid haze, sheltered from the inferno below. It is an old and speculative idea, and it received a jolt of attention when a team announced that they had detected, in the clouds of Venus, a gas called phosphine. On Earth, phosphine is associated with life, produced by certain microbes, and it was not clear how it could be present on Venus in the amounts claimed without some unusual source, possibly a biological one. The announcement set off a vigorous and ongoing scientific argument, and that argument is itself worth understanding, because it shows how science handles an extraordinary claim. Almost at once, other researchers questioned the detection. Some reanalyzed the original data and concluded that the signal was weaker than reported, or perhaps not there at all, possibly confused with the signature of another, more ordinary gas. Some found the amount of phosphine, if it was present, to be far lower than first claimed. The original team, for their part, continued to gather data and to defend the presence of the gas, while acknowledging the difficulty of the measurement. Years later, the question remains genuinely unsettled. It is not clear whether phosphine is truly present in Venus's clouds in significant amounts, and even if it is not clear that life would be the explanation, for there may be chemistry on Venus, still poorly understood, that could produce it without any living thing at all. The phosphine on Venus is not evidence of life. It is a disputed signal that reopened an old question and prompted new plans to study the planet more closely. That is all it is, and that is nothing, but it is far less than a discovery. What Venus illustrates, better perhaps than any other case, is the pattern that runs through this entire search. A signal appears, surprising and suggestive. Hope rises, and then the slow, careful, sometimes deflating work of science sets in. The checking and rechecking, the search for ordinary explanations, the demand for evidence strong enough to bear the weight of so extraordinary a conclusion. Most such signals fade under that scrutiny, or dissolve into ambiguity, or wait, unresolved, for better instruments and further study. This is not a failure. It is exactly how a careful mind should approach the most important question it can ask. The universe is under no obligation to give up its answers easily, and the answer to this question, if it comes at all, will have to be earned, one careful measurement at a time. Everything so far has stayed within our own solar system, among the worlds close enough to visit with machines, to photograph, to sample, to touch. But these are a tiny handful of worlds, circling a single ordinary star in a galaxy of hundreds of billions of stars, in a universe of hundreds of billions of galaxies. The great majority of the search must be conducted at a distance so vast that visiting is out of the question, using nothing but the faint light that crosses the gulf between the stars. And it is here, in the study of worlds beyond our sun, that the last several decades have brought a transformation so complete that it is easy to forget how recent it is. Within living memory, no one knew whether any other star had planets at all. It seemed likely, but it was not known. The planets of other stars, if they existed, were far too small and faint to see directly, lost in the overwhelming glare of the stars they orbit. Then, near the end of the 20th century, astronomers found the first of them, and the discoveries have not stopped since. Today, the count of confirmed planets beyond our solar system stands above 6,000, and it climbs steadily as the surveys continue. 6,000 worlds, and every one of them found in the last few decades, where before there were none. They come in every variety. Giant balls of gas larger than Jupiter, circling so close to their stars that their years last only days. Worlds of rock and worlds of ice. Planets larger than Earth, but smaller than Neptune, a size that has no example in our own solar system, yet appears to be among the most common in the galaxy. And scattered among them, worlds that are roughly the size of Earth, orbiting at roughly the right distance in the habitable zones of their stars. The trick that made this possible is ingenious in its simplicity. Most of these planets have never been seen. They are detected instead by their effects. The most productive method watches for a tiny, regular dimming of a star's light. If a planet's orbit happens to carry it directly between its star and us, then once each orbit, it passes across the face of the star, blocking a minute fraction of the light, casting a shadow toward Earth. By watching thousands upon thousands of stars at once, patiently, for the faint periodic dips that betray a passing planet, astronomers have found world after world, and the amount of light blocked reveals the size of the planet, while the timing reveals the size and shape of its orbit. And so a great deal can be learned about a world that has never been seen at all, from nothing more than the rhythmic flickering of a distant star. But knowing that a planet exists, and knowing its size and its orbit, is a long way from knowing whether anything lives there. For that, astronomers must go further and reach for something that seemed, not long ago, almost impossible. They must study the air of these distant worlds. When a planet passes in front of its star, a little of the starlight filters through the thin ring of the planet's atmosphere on its way to us, and the gases in that atmosphere leave their marks on the light, each kind of molecule absorbing particular colors, subtracting its own signature from the spectrum that reaches our telescopes. By reading those signatures with great care, astronomers can begin to work out what a distant world's atmosphere is made of, even across a distance of many light years. It is a delicate and difficult measurement, at the very limit of what the finest instruments can do, but it opens a door that was closed for all of history until now. It lets us ask, of a world we will never visit, what it is breathing. And this is where the concept of a biosignature comes into its own. A biosignature is a sign of life, something in the light of a distant world that would be difficult to explain without living things. The classic example is the combination of gases in Earth's own air. Our atmosphere is rich in oxygen, and oxygen is a restless, reactive gas that, left alone, would soon disappear, combining with rocks and other elements until it was gone. The only reason Earth's air stays full of oxygen is that life keeps replenishing it, plants and other organisms pumping it out faster than it can vanish. An alien astronomer, studying the light of Earth, might see the abundance of oxygen and recognize it as a puzzle that only life could easily solve. So the hope has been that we might do the same in reverse, that we might find, in the air of some distant world, a combination of gases so out of balance, so difficult to sustain without life, that life becomes the most reasonable explanation. It is harder than it sounds, and a recent episode shows just how hard. Some years ago, attention fixed on a particular distant world, a planet larger than Earth and smaller than Neptune, circling a small, cool star more than 100 light-years away. Studies of its atmosphere suggested it might be a world of a kind not found in our solar system, possibly with a deep ocean of water beneath a thick atmosphere rich in hydrogen. And then a team reported something that set the field alight. In the light passing through that world's atmosphere, they believed they had detected the faint signature of a particular gas, a sulfur-bearing compound that, on Earth, is produced almost entirely by living things, by tiny organisms in the sea. If that gas were truly present, and if it were truly the product of life, it would be a discovery beyond measure. The team was careful in their language, calling it the strongest hint yet of possible biological activity on a world beyond our own, but stopping short of claiming they had found life. What happened next is a portrait of science at its most rigorous and its most humbling. Other researchers took the same data and analyzed it with their own methods, and many of them could not find the signal at all, or found it far weaker than claimed. They pointed out that the feature in the light was faint, close to the level of the instrument's own noise, and that other gases could produce a similar signature, so that the detection was not unique. They noted, too, that the reasoning rested on a chain of assumptions about the nature of the planet and about the source of the gas, each of which could be questioned, and they observed that the very compound thought to be a sign of life has also been found in places where there is certainly no life, in comets and in the cold clouds between the stars, which means that even its presence, if confirmed, would not by itself prove anything living. The scientific community has a demanding standard for a claim of this magnitude, a level of statistical confidence far beyond what this signal reached. And by that standard, the honest verdict is that no convincing evidence of life has been found on that world. The signal remains, at best, a tantalizing and disputed hint, a reason to keep looking, not an answer. The debate continues, careful and unresolved, exactly as it should. There are other worlds that draw the eye as well, and one system in particular has become a favorite target. Around a small, dim, cool star about 40 light-years away circle 7 planets, all of them roughly the size of Earth, packed into orbits so tight that the entire system would fit comfortably inside the orbit of Mercury around our Sun. Several of these 7 worlds fall within their star's habitable zone, at distances where liquid water might, in principle, exist. It is a remarkable arrangement, a miniature solar system of Earth-sized worlds, close enough to study and rich with possibility. Yet even here, the honest picture is one of uncertainty. The most promising of the 7, a world near the middle of the habitable zone, would only be habitable if it possessed an atmosphere to hold in warmth and permit liquid water. And whether it has an atmosphere at all remains, at the present time, unknown. Careful observations have been made, and more are underway. but the results so far have not been able to say for certain whether the planet has any air, or whether faint hints of it are real signals or merely noise from the restless star it orbits. The little star is prone to flares, to violent outbursts of radiation that could, over time, strip the atmospheres from its close-orbiting worlds. So the question hangs open, a system of Earth-sized planets, tantalizingly near, and we cannot yet say whether any of them hold so much as a breath of air. This is the state of the search among the stars. Thousands of worlds discovered, an achievement that would have seemed miraculous a lifetime ago. The ability, newly won, to study their atmospheres across the void. And yet, as of now, not a single confirmed sign of life anywhere among them. Hints, yes. Candidates, debates, disputed signals, worlds that deserve a closer look. But no answer. The instruments grow more powerful with each passing year, and the day may come when a signal arrives that survives every test, that cannot be explained away, that stands up under the full weight of scientific scrutiny. If it comes, it will be one of the most significant moments in the history of our species. But it has not come yet, and the search goes on in the meantime, patient and unhurried, reading the light of distant worlds for the faint chemistry of the living. It is worth pausing here to ask a question that often gets lost beneath the excitement of the search. If life were found somewhere out there, what would it most likely be? The images that fill the imagination tend toward the dramatic. Beings with minds and machines, cities and voices, creatures that could be spoken to or reasoned with or feared. But the sober expectation of the people who actually study this question points somewhere far quieter, and the reason lies once again in the history written into our own planet. For the overwhelming majority of the time that life has existed on Earth, it was microscopic. Life arose more than 3 billion years ago, and for the first 2 billion of those years, and more, it consisted of nothing but single cells, invisible to any eye, drifting and dividing in the ancient seas. There were no plants, no animals, no creatures of any size at all. The world was alive, but its life was small, a planet of microbes and nothing else, for a stretch of time so long it dwarfs everything that came after. Only relatively late in the story did life grow complex. Only later did cells learn to join together into larger bodies. Only late did anything crawl onto land, or grow a backbone, or open an eye. And only in the very last sliver of that immense history, a blink at the end of a very long day, did there appear a creature capable of looking up at the stars and asking whether it was alone. The lesson in this is sobering and clarifying at once. Life, where it exists, may be common, but complex life, life large enough to see, may be far rarer, a later and more difficult achievement. And intelligent life, life that builds and wonders and asks questions, may be rarer still, perhaps extraordinarily so. If life is found beyond Earth in the coming years, the odds strongly favor its being microbial, a film of single cells in a Martian rock, a haze of microbes in the clouds of some distant world, a slick of living chemistry at the bottom of a sealed ocean on a frozen moon. Not a civilization, not a voice. Something small and simple and unspeakably profound, because even the simplest living cell beyond Earth would answer the deepest form of the question. It would tell us that life is not unique to our world, that the spark can catch more than once, that we are not, in the largest sense, alone. A single alien microbe would be, in its way, as momentous as any imagined empire among the stars. And even that simple life might be difficult to recognize, because it might not be built the way we are built at all. This is where the search brushes up against the limits of imagination, and where the earlier struggle to define life returns with new weight. All the life we know shares a common chemistry. It is built on carbon. It runs in water. It stores its instructions in the same few kinds of molecules. But this shared chemistry might reflect nothing more than shared ancestry. Every living thing on Earth appears to descend from a single origin, a common root far back in time. And so, of course, they all share the same fundamental design. It tells us how the one life we know is built. It does not tell us how life must be built, everywhere and always. So scientists have allowed themselves to wonder about alternatives, always carefully, always marking the boundary between what is known and what is merely conceivable. Might life somewhere be based not on carbon, but on some other element? Silicon is the candidate most often raised because it sits just below carbon in the ordering of the elements and shares some of its ability to form bonds. But silicon is a poorer builder than carbon, its bonds less versatile, its compounds less stable in the conditions where liquids flow. And most researchers doubt it could support the intricate chemistry that life requires. Carbon seems genuinely special, not merely familiar. Might life use a liquid other than water? This seems more plausible, and Titan, with its seas of methane, is the standing invitation to take the idea seriously. Might life store its information in molecules different from ours, or capture energy in ways we have not thought of? All of this is possible. None of it is known, and the great danger in all of it is the one named at the very beginning: the danger of looking only for ourselves, of building our instruments and framing our questions so narrowly around the life we know that we would walk past a stranger form without ever noticing it was there. There is an idea at the far speculative edge of the field that makes this danger vivid. It has been suggested that life might have arisen on Earth more than once, in more than one distinct origin, and that a second kind of life, descended from a separate beginning and built on a subtly different chemistry, might still exist here on our own planet, overlooked. A shadow form of life, hidden among the familiar microbes, is missed because our tools are designed to detect life like ours and might simply fail to see anything else. There is no evidence that such a shadow life exists. It may well not. But the very fact that it cannot yet be ruled out on our own thoroughly studied world is a striking measure of how much we still do not know, and of how careful we must be. If a second Genesis could hide undetected on Earth, then we must be humble indeed about our ability to recognize life on a world we can only glimpse from afar. The search for life beyond Earth is, in part, a search for the wisdom to know life when we finally meet it, in whatever strange dress it wears. This is why the study of life's origins and the study of extremophiles matter so much to the search among the stars. They are attempts to loosen the grip of our own example, to learn what about earthly life is essential and what is merely accidental, so that when we look outward, we look with clearer eyes. Every hardy microbe found in some impossible place on Earth, every new idea about how life might have begun, every experiment that makes a building block of life from simpler stuff, widens the frame through which we see. The search for alien life is not only a search of the sky. It is equally a search of our own biology, our own chemistry, our own planet, for the clues that will tell us what to expect and how to recognize it. We understand the possible only through the actual, and the only actual life we have is here, beneath our feet, and in our own bodies, waiting to be understood well enough to serve as a guide to the unknown. And so the question that began this account deepens as it goes. What is extraterrestrial life? It is, first of all, something we have never found, a possibility rather than a fact, held open by everything we know about chemistry and closed by everything we have so far failed to observe. It is, most likely, if it exists at all, something small and simple, microbial, ancient, patient, the kind of life that filled our own world for billions of years before anything larger stirred. It is something that might be built like us, on carbon and water, or something built on foundations we have barely begun to conceive of. It is a thing we are straining to detect across distances that defeat the meaning of the word far, using the faint light of passing worlds and the slow, careful work of many minds across many years. And it is, above all, a question that we do not yet have the power to answer, but that we have, for the first time in the history of our kind, gained the power to genuinely ask. There is one more path in this search that runs alongside all the others, distinct in its method, though joined to the same great question. Everything described so far has been a search for life through its chemistry, for the faint traces that any living thing, however humble, would leave in the rock or the water or the air. This is the search for biosignatures, and it makes no assumption that the life in question can think, or build, or intend anything at all. A microbe leaves a biosignature simply by living, but there is a second and stranger kind of sign that only a particular sort of life could leave, and that is the sign of technology. A civilization, if one existed, might do things that no microbe could. It might send signals across space, deliberately or as a byproduct of its own activity. It might reshape its world, or its star, in ways that could be detected from afar. These possible fingerprints of intelligence are called technosignatures, and the effort to find them is a search not merely for life, but for minds. For more than half a century, in a quiet and often thankless endeavor, some astronomers have listened. They have turned great dishes toward the stars and swept across the radio frequencies, hoping to catch some signal that could not be natural, some pattern too ordered to be the work of physics alone, a message or a leakage from a distant civilization. It is a search built on a slender hope, and it has, so far, heard nothing that could be confirmed as artificial. Once, decades ago, a telescope caught a strong and startling burst of radio noise that fit some of the expectations for such a signal, and it has never been explained nor ever heard again. A single, unrepeated anomaly that has haunted the field ever since. But one unexplained blip, unrepeatable, is not a discovery. It is a question mark hanging in the record. The listening continues, patient and unrewarded, sustained by the knowledge that a single confirmed signal would change everything, and by the recognition that the only way to hear such a thing is to keep listening even through the long silence. The search for minds is harder than the search for life, and rests on far more assumptions. Life might be common while intelligence is vanishingly rare. A civilization might exist, but never send a signal, or send one we cannot recognize, or have flourished and fallen long before its light could reach us, or lie so far away that no signal could ever cross the distance in any span of time that matters. The silence we have heard so far tells us something, though it is difficult to say precisely what. It may mean that no one is broadcasting. It may mean that we have not listened long enough, or in the right way, or to the right places. It may mean a great many things, and untangling them is a delicate matter, one where it is easy to read too much into the quiet. What can be said with confidence is only this: we have looked in the ways available to us, and we have not yet found company. The rest remains open. Between these two searches, the search for the chemistry of simple life and the search for the signals of complex minds, lies the whole range of what extraterrestrial life might turn out to be. And spanning that range is the same fundamental uncertainty, the uncertainty that comes from having only one example to reason from. We do not know how easily life begins, because we have watched it begin only once, and even that once we cannot fully explain. We do not know how often simple life, having begun, goes on to become complex, because in our own world it happened a single time and took an unimaginable stretch of years to do so. We do not know how often complexity leads to intelligence, because again, we have but one case ourselves. At every step of the chain, from lifeless chemistry to living cell, from simple cell to complex creature, from complex creature to questioning mind, we are working from a sample of one, and a sample of one, as any careful thinker knows, can support almost any conclusion and prove almost none. This is why the coming years hold such promise and such genuine suspense. The instruments now being built and planned are more powerful than any that have come before. New telescopes, in space and on the ground, are being designed specifically to study the atmospheres of small, rocky, Earth-like worlds around other stars, to read their air for the telltale imbalances that might betray life. Missions are being prepared to visit the ocean moons, to fly through the plumes of the little worlds that spray their hidden seas into space, to land on the strange chemical plains of Titan, to bring home, if it can be managed, the cached rock from Mars that may or may not hold the trace of ancient life. Each of these is a chance, however slim, to find the second example that would transform everything. And the beauty of it is that we do not know which one, if any, will succeed, or when, or how. The answer might arrive in a laboratory studying a returned sample. It might arrive in the analysis of starlight filtered through an alien atmosphere. It might arrive from a place no one is watching closely, in a form no one predicted. Or it might not arrive at all, not in our lifetimes, not for a very long time, the silence stretching on as it has stretched so far. It is worth sitting for a while with both of those outcomes, the discovery and the silence, because each carries its own meaning, and neither is empty. Consider first what it would mean to find life. Not a civilization, necessarily, not a signal, but simply life in any form, anywhere beyond Earth. A colony of microbes in a Martian rock, a trace of living chemistry in an alien sea. A single confirmed sign in the atmosphere of a distant world that could be explained only by living things. Such a finding would settle, in a single stroke, a question that human beings have asked for as long as there have been human beings to ask it. It would tell us that the origin of life is not a miracle confined to one world, but a natural event, repeatable, woven into the ordinary workings of the cosmos. It would mean that the universe is, in some real sense, fertile, disposed to bring forth life wherever the conditions allow. And it would place us, at last, in a context. We would know ourselves to be one instance of a general phenomenon, not a singularity, but an example, kin to whatever else is out there, sharing with it the deep, strange fact of being alive in a universe that did not have to permit it. The discovery would also, quietly, reshape how we see ourselves. For all of history, life has been the thing that set our world apart, the quality that made Earth precious and unique against the dead backdrop of space. To find life elsewhere would not diminish the preciousness of life. If anything, it might deepen it by revealing life as one of the universe's great themes rather than a lonely exception. But it would end a certain kind of solitude, an isolation that has shaped every myth and every faith and every philosophy our species has ever produced. We have always understood ourselves as the living world set against the lifeless heavens. To learn that the heavens themselves are, here and there, alive, would be to rewrite the oldest story we tell about our place in things. It would be one of those rare discoveries that changes not just what we know, but who we take ourselves to be. And yet the silence, should it continue, is not without meaning of its own, and it is a mistake to treat the absence of a discovery as merely a failure or a disappointment. If we search carefully and long across many worlds and by many methods and we find nothing, that too is information, and it too has weight. It might tell us that life is genuinely rare, that the step from lifeless chemistry to the living is far harder than the speed of life's arrival on Earth would suggest, that we are, if not alone, then at least uncommon, scattered so thinly across the vastness that we may as well be solitary. There is a kind of sorrow in that possibility, but there is also a kind of grandeur and a heavy responsibility. For if life is rare, then it is all the more precious, and the life on our own world, this improbable flourishing of green and blue on a small rock circling an ordinary star, becomes something close to sacred, a rare and fragile thing to be guarded rather than squandered. The silence, if it is real, would tell us that what we have here is not the common stuff of the universe but its rarest achievement, and that the care of it falls to us. Both outcomes, then, teach humility, and both teach a kind of reverence. The discovery would humble us by placing us among others. The silence would humble us by revealing how easily there might have been nothing at all, how thin the margin by which we came to exist. And running beneath both is the vast fact that gives this whole question its depth, which is the fact of time. For the universe is very old, older than the mind can truly hold, and the Earth and its life occupy only the most recent portion of that immense span. The universe existed for billions of years before the Earth formed. The Earth existed for billions of years, alive with microbes, before anything complex appeared. And human beings, with their questions and their instruments and their yearning to know whether they are alone, have existed for the merest flicker at the very end, a span so short against the age of the cosmos that it hardly registers at all. We are latecomers, asking an ancient question, in a universe that has been quietly keeping its own counsel for ages beyond counting. That deep time cuts in more than one direction, and it is worth following where it leads. If life is common, then it has had ample time to arise on countless worlds, and some of it may be far older than we are, having begun on planets that formed long before the Earth, around stars that are older than our sun. There may be life out there that is billions of years more ancient than the life on Earth, that arose while our world was still a ball of molten rock, that has been going about its quiet business for longer than our planet has existed. And equally, there may be worlds where life is only now beginning, where the first self-copying molecules are stirring in some warm, dark sea, taking the same first steps that were taken here so long ago. The great story of life, if it is a story that plays out across the universe and not only here, is not synchronized. It runs at different points on different worlds, some ancient, some just beginning, most of it, if it exists, forever beyond our reach and our knowing. We are watching for it from a single moment, on a single world, with instruments we have possessed for only the briefest time. That we can watch it all is remarkable. That we might miss almost everything is simply the nature of our situation, small observers in an enormous and ancient place. And there is a further thought, quieter still, that the deep time invites. Whatever we find or fail to find, the search itself is a kind of answer to the question of what we are. For here is a species, arisen late on an ordinary world, that has looked at the dead and silent sky and refused to accept its silence as final, that has built instruments to read the air of worlds it will never touch, and sent machines across the solar system to taste the plumes of frozen moons, and listened, year after year, for a signal that has never come, that has taken the one example of life it possesses, its own, and studied it deeply enough to begin imagining forms of life it has never seen. This searching is not driven by necessity. Nothing about our survival requires that we know whether there are microbes in the clouds of Venus or in the seas beneath the ice of Europa. The search is driven by something else, something harder to name, a need to understand, to place ourselves, to know whether the great fact of being alive is ours alone or shared. And in a universe that appears so far to be silent, searching may be among the most distinctly living things about us. Life reaching out across the dark to look for other life. For now, the looking continues without an answer. The great question stands where it has always stood, open, unresolved, held between the hope of company and the possibility of solitude. We know more than we have ever known, and we know how little that is. We have found the ingredients of life scattered through the cosmos, and no life to go with them. We have found worlds beyond counting, and no clear sign of anything living on any of them. We have found on our own world that life is harder and stranger than we ever supposed, and we have carried that lesson outward, unwilling to call any place dead until we have truly looked. And we have learned, above all, to hold the question gently, to resist the pull toward easy answers in either direction, to let the evidence be what it is and no more. The universe has not told us whether we are alone. It has only given us the tools at last to ask, and the patience, if we can summon it, to wait for whatever answer the long years may bring. There is a dimension to all of this that is easy to overlook when the focus falls on ingredients and distances, and it is the dimension of time. Life did not merely need the right conditions on the early Earth. It needed those conditions to last. The arrival of the first living things was only the beginning of a story that then had to continue, uninterrupted, for billions of years, through every upheaval the planet could throw at it, without ever once being extinguished entirely. And this requirement, that a world remain habitable not for a moment but for ages, turns out to be a demanding one, perhaps more demanding than the mere presence of water and warmth. A world can be habitable and then cease to be. A world can hold life briefly and then lose it. And the difference between a world where life flickers and dies and a world where it takes hold and endures may come down to a whole set of conditions that have nothing to do with distance from a star. Mars is the cautionary example, close at hand. It seems once to have had water, warmth, and the ingredients of life, everything that the young Earth had. And yet Mars, being a smaller world, could not hold on to what it had. Its interior cooled. Its protective magnetic field faded. Its atmosphere, no longer shielded, was slowly stripped away by the wind of particles that stream from the sun, until the air grew thin and the water fled or froze. Whatever chance Mars had for life, if it had one, was a chance that closed. The window opened, and then, over long ages, it shut. If life ever arose there, it may have been snuffed out as the world it depended on grew cold and dry around it. Mars shows that being briefly habitable is not enough. A world must stay habitable, and staying habitable is a matter of the world's whole nature. Its size, its warmth within, its ability to hold an atmosphere and shield itself and maintain, across immense spans of time, the gentle conditions that life requires. Earth, by contrast, has managed the extraordinary feat of remaining habitable, more or less continuously, for billions of years, through ice ages and warm ages, through great volcanic upheavals, through the slow drift of continents and the crash of asteroids, through catastrophes that wiped out great fractions of living things, and yet never quite extinguished life itself. How our world has managed this is a question that draws on the whole of the sciences, and the answers point to a delicate balance of many factors working together. A steady star, neither too violent nor too dim, burning evenly across the ages. An interior that stays warm and active, driving the slow recycling of the crust that helps regulate the climate over long stretches of time. A magnetic field that deflects the worst of the radiation from space and helps the atmosphere endure. A stock of water, neither so little that the world dries nor so much that it drowns. Even the presence of the moon and of the great planets farther out may play some role in steadying the conditions of our world. None of these by itself is the secret. It is their combination, their long cooperation, that has kept the Earth a place where life could persist and slowly build upon itself. This complicates the search in a way that is sobering, but important to hold clearly. It is not enough to find a world at the right distance from its star. It is not even enough to find a world with water and warmth and the ingredients of life, to find a world where life could truly take hold and endure. One would want a world that has held those conditions steady across the ages, and that is a far more difficult thing to assess from a distance, and a far rarer thing, perhaps, than a world that is merely habitable at a glance. Many of the worlds now being studied circle small, cool stars, the most common kind of star in the galaxy, and such stars have a habit of flaring violently, especially in their youth, bathing their close-orbiting worlds in bursts of radiation that could strip away atmospheres and sterilize surfaces. A world in the habitable zone of such a star might have water in principle, and yet be scoured bare in practice. This is why the question of whether a given distant world even has an atmosphere matters so much, and why so much effort goes into that single, difficult determination. An atmosphere is not merely a convenience. It is, in a sense, the sign that a world has been able to hold on to itself, to keep its air against the erosion of space and time. And a world that cannot keep its air is unlikely to keep its life. So the picture that emerges when all of it is held together is neither simply hopeful nor simply bleak. It is layered, and it is honest. The ingredients of life are common, spread through the cosmos, forming readily wherever the conditions allow. Habitable places, in the loose sense of worlds with water and warmth, may also be common, scattered through the galaxy in great numbers, including in the hidden oceans of frozen moons far from any star. But worlds that are not merely habitable in a moment but habitable across the ages, stable enough and sheltered enough and steady enough for life to arise, and then to persist and slowly grow complex. These may be considerably rarer and harder to identify and harder still to study. And whether life, given all of that, actually begins. Whether the crossing from lifeless chemistry to the living thing happens easily or almost never, remains the great unknown at the heart of it all. The one thing our single example cannot tell us. The universe on this reading may be a place full of the promise of life, and full of the settings where life could take hold, and yet still, for reasons we do not understand, quiet, or it may be teeming in ways we have not yet learned to see. The honest answer is that we do not know, and that not knowing, held gently and without despair, is itself a kind of wisdom. What can be said is that the search has already given us something of great value, quite apart from any discovery it may one day make. It has given us a truer sense of our own world. To ask what life requires, and where else it might arise, is to look back at the earth with new eyes and to see, perhaps for the first time, how remarkable it is. Not because it is necessarily unique, but because it is, at the very least, the one place we know for certain where the improbable happened, where matter woke into life and life in time woke into awareness. Every study of distant worlds returns us, in the end, to this one. Every list of the conditions life needs is, in truth, a description of home. The search outward is, in a quiet and unexpected way, a long meditation on the place we already stand, on the thin blue film of air and water and living things that wraps our small planet, on the astonishing and easily forgotten fact that here, at least, in this one corner of an enormous and largely empty universe, the dark somehow gave rise to the living. Perhaps it helps, as the night deepens, to gather the whole of the search into a single quiet view, to hold in the mind at once all the places where the question is being asked. Somewhere out there, a small rover sits on the surface of Mars, its work of drilling done, a sealed tube of ancient rock resting within it, a rock that carries patterns that life could have made and may have made, waiting through the long red dusk for a journey home that has not yet been arranged. Somewhere out there, a spacecraft crosses the immense dark between the planets, still years from its destination, carrying instruments meant to study the frozen shell of an ocean moon around distant Jupiter, to learn whether the sea beneath that ice could hold anything living. Somewhere out there, the little moon Enceladus goes on quietly spraying its hidden ocean into space, its plumes rising and falling, its secret carried outward into the ring of Saturn, whether or not anyone is there to read it. Somewhere out there, Titan turns beneath its golden haze, its methane rivers flowing, its strange chemistry unfolding in the deep cold, awaiting the arrival of a machine that will fly across its skies and set down upon its plains. And far beyond all of these, beyond the edge of our own small family of worlds, thousands of distant planets circle their own stars, and a handful of them, studied with the greatest care we can bring to bear, hold hints and puzzles and the faint possibility of an atmosphere, a possibility that we cannot yet confirm or deny. None of these has given us an answer. Every one of them holds open a question, and that, in truth, is where the whole matter rests tonight, and where it has rested for some time. The search is broad and patient and ongoing, spread across many worlds and many methods, conducted by many minds over many years. And it has not yet found what it seeks. It has found the ingredients everywhere, and the thing itself nowhere. It has found candidates and hints and disputed signals, each one carefully weighed and, so far, each one falling short of the certainty the question demands. This is not discouragement. It is simply the honest state of things, the map as it actually stands without embellishment, We are looking. We have not found. We continue. And there is a particular kind of peace to be found in that honesty, if one is willing to receive it. The question of whether we are alone is one that human beings have carried for a very long time. And for nearly all of that time, it was a question that could only be wondered at, never investigated, a matter for myth and imagination and longing. It is only now, only in the most recent moment of the human story, that the question has passed into the hands of science, that it has become something we can actually pursue with instruments and evidence, rather than only dream about. That transition from wondering to searching is itself a quiet marvel, easy to overlook amid the impatience for a result. Whatever the search finds or fails to find, it represents a species that has grown able, at last, to ask its oldest question in a way that might one day be answered. And to have reached that point after so long is no small thing. The answer, when and if it comes, will not come with the drama that the imagination supplies. It will not be a voice from the sky or a ship descending or a face at the window. If it comes at all, it will most likely come as a line on a graph that survives every attempt to explain it away, or a chemical signature in the light of a distant world that finally passes every test, or a pattern in a returned Martian rock that no lifeless process can account for. It will come quietly, in the language of measurement and evidence, and it may take years for the scientific community to agree on what it means. The great discovery, if there is to be one, will arrive not as a thunderclap, but as a slow and careful and hard-won certainty, built up measurement by measurement, until the weight of it can no longer be denied. And on that day, whenever it may be, the universe will feel forever after a little less empty than it does tonight. Until then, the ingredients drift through space, the worlds turn in the dark, the instruments listen and watch, and the question remains open, held gently in the quiet, waiting. So let the question settle now, the way dust settles in a still room, the way the light fades slowly from the western sky. There is no answer to reach for tonight, and no need to reach. The world will keep turning whether or not we resolve them. The frozen moons will keep their oceans sealed beneath the ice. The distant planets will keep crossing the faces of their stars, casting their small shadows toward us across the enormous dark, indifferent to whether we are watching. And somewhere, perhaps, on a world we will never name, in a sea we will never sail, something small and living may be going quietly about the business of staying alive, as unaware of us as we are of it. Or perhaps not. Perhaps the living universe begins and ends, for now, with this one pale world and the fragile film of life upon it. Either way, the not knowing can be held softly, without strain, the way one holds any old and beautiful mystery, content to let it remain a mystery a little while longer. Think, as the mind grows slow and heavy, of the sheer patience of it all. The universe has waited billions of years and shows no sign of hurrying. The ingredients of life have drifted through the cold clouds between the stars since long before the Earth existed, and they drift there still, unhurried, in no rush to become anything at all. Light from the worlds we study has traveled for years, for decades, for centuries across the emptiness to reach our instruments, carrying its faint chemical messages at a pace set by the ancient geometry of space. Everything about this question moves slowly. The gathering of the ingredients, the crossing into life, the long, dim ages of the microbial world, the rare and gradual climb toward complexity, the even rarer flicker of awareness at the very end. It is a story told across spans of time so vast that any single life, any single night, is less than a heartbeat within it. And there is comfort in that, a strange and gentle comfort, in belonging to something so much larger and older and slower than oneself, in being one brief living moment in a process that reaches back to the beginning of everything. The search for life beyond Earth is, in the end, an act of quiet hope carried out in the face of a mostly silent sky. It asks the darkness whether anyone else is there, and the darkness, so far, has not replied. But the asking goes on, gently, generation after generation, and the instruments grow keener, and the list of places to look grows longer. And each year we understand a little more about what life is, and where it might hide, and how we would know it. There is no urgency in it, or there need not be. The answer, if it exists, has waited this long and will wait a little longer. What matters is that the looking continues, that the question stays open and alive, passed carefully from one patient set of hands to the next, like a small light carried through a long, dark hall. If these slow wanderings through the question of life among the stars are the kind of thing that brings you a measure of calm, that quiets the mind as the day lets go, then you are welcome to stay a while longer with this small and growing collection of nighttime journeys. And a gentle follow, or a quiet note left behind, helps these contemplations find the others who go looking for stillness in the dark. But there is no need to reach for anything now. That can wait for the waking hours, or need not happen at all. For now, there is only this: a small world turning slowly in the night, a sky full of distant suns, and around them worlds beyond counting, most of them silent, all of them far. A question as old as wonder itself, held softly, unanswered, and somehow the more beautiful for remaining so. The ingredients of life scattered like faint seeds across the whole immense reach of space, waiting in the cold and the dark, and the long, slow turning of time, for conditions that may come or may not. And here, on this one world where the improbable happened, a single quiet mind, drifting now towards sleep, having looked out for a while into the vastness, and having found there not an answer but something almost better, the deep and settling knowledge that the looking itself is enough, that it is a good thing to have wondered, and that the stars will keep their silence kindly through the night, and be there, unchanged, when the morning comes. Rest now. The universe is old and patient and in no hurry at all. The question will remain, and the dark, for all its emptiness, is a gentle place to close the eyes.